updates every 5 minutes. For very short-range NWP, we use deterministic and ensemble high-resolution model. Currently, still our Cosmo D2 and EPS, and soon we will have an Icon LAM version here. Again, you see on the left-hand side, on the right-hand side, the observation and a deterministic Cosmo forecast. These methods, of course, are rather expensive. New forecast available only 1 to 1.75 hours after the actual date. New forecasts are set up every 3 hours and run to plus 27 or plus 48 hours. Up to now, these methods have been developed quite separately, and there also exist no common products. So this means we do not have a seamless transition, and this also exemplifies in our HIWeather app, which is shown here on the right. So this is basically what the users outside get on precipitation fields, and on the left part, you see what stems from Nowcasting. On the right hand, you see what stems from the NWP, and you clearly see that there is a real cut between the two. And this cut we want to eliminate as good as possible with our SINFONY system. So the basic idea can be explained on this score plot. So you assume some verification score for convective events. We have the Nowcasting, which is really good, performing at short lead times, but drops down at later lead times. You have NWP, which starts earlier than the actual date, which is initialized earlier than the actual date, starts with a lower score, but at the end outperforms Nowcasting at longer lead times. And at one point, you have the intersection where both show the same score. On the one hand, with SINFONY, we now aim to improve our Nowcasting methods themselves. We also want to improve and expand our NWP. So with overall, we get a better skill of both of them. And then we also develop some combined products that seamlessly bring together the best information from both worlds into a mostly seamless product. At the moment, the focus is put here on precipitation forecasts. And so the mission is to complement, further develop, and interlock products of Nowcasting and NWP in such a way that a seamless representation of the atmospheric state and weather phenomena from now until 6 to 12 hours becomes possible. For the Nowcasting, this means, so in black you see the current data that is used for Nowcasting, and in red what's new or in addition with SINFONY. So we want to switch from two-dimensional to volume radar data. We also include lightning, and we also include cell objects from the NWP model. So with cells, we mean convective cells that have been identified by an algorithm in the NWP forecast. So this cell algorithm detection is something that we usually used for Nowcasting. I will come to it in a minute, and we will now also employ it on model data. Then the system and approaches are, on the one hand, an optimized optical flow and switching from a deterministic to an ensemble ansatz here. And also for the cell objects, we consider the typical life cycle of convective cells and try to get an estimate about the future intensification or weakening. This means our future precipitation forecast for the Nowcasting part will be a Nowcasting ensemble for gridded field precipitation and also for cell objects from 0 to 6 hours. For the optical flow radar Nowcasting ensemble, we use elements of the STEPS system that has been used at many other weather services already, and some of you might be familiar with it. We call it STEPS DWD because we have made some refinement concerning localizations. So the basic idea of this approach is you have the observation. From the radar data, there you eliminate the ever-growing unpredictable scales through a scale decomposition and autocorrelation timescales. So with this, you get a forecast of the predictable of the situation, so basically a deterministic information. And this is now what is kind of predictable from that situation. And then you replace the unpredictable scales by several realizations of suitable correlated noise. And with this, you get a grid-based SINFONY Nowcast ensemble. In the middle is now shown one ensemble member as an example. And we run this with 20, sometimes also with 30 or 40 members. We will see how many we can afford in the end. And this ensemble then also allows you to derive information about ensemble spread, which on the right hand is shown now, and in particular the regions and the boundary regions of these convective events are prone to larger ensemble spread in that case. And this is also a collaboration we are doing together with colleagues from Meteo Swiss, and also want to thank them for their support here. The other one is the object-based SINFONY Nowcasting ensemble I talked about already. This is based on our Conrad 3D. So objects is kind of a simplified but still a three-dimensional representation of a convective cell. Then we use a cell detection and tracking algorithm applied to our 3D volume scans of the radar. Up to date, this is just a deterministic linear advection of the cells, but also with some uncertainty cone information. This is shown on the right. And as part of SINFONY, now use an first guess parabola ensemble, which kind of represents the climatological median cell size for convective cells over Germany. So there has been a study on which kind of line or curve represents best the life cycle of convective cells over Germany. And we found this parabola to be a pretty good first guess in some cases. And this is then also successively corrected by an ensemble Kalman filter. In the future, we also want to explore refined or more advanced mathematical models for the first guess, and potentially also connected to environmental conditions from NWP. So here you see an example of this object-based SINFONY Nowcasting ensemble. On the bottom, you see the cell size, and on top, you see the ensemble. So this is kind of how this ensemble Kalman filter corrects for the cell size. And the red lines basically show where the different ensemble members propagate their cells. And you can also then combine this information to make a probability to see what's the most probable, the most likely track the cell will take up in the future. So for the convection resolving NWP, we will add information from Severi satellite data. We also work on assimilating lightning. And this makes the connection between Nowcasting and NWP. We also work on assimilating the cell objects we identified in the Nowcasting. This will then put into our icon model, and we also working on setting up a so-called rapid update cycle version of icon. So it's an icon APS that will run every hour for 0 to 12 hours, also with improved model physics. For example, we are switching to the two-moment microphysics scheme here because it's a better representation there of the convective cells, as we found. So just briefly go through our model chain. So we have the global EU, then we have a global icon, then we have the icon EU with 6.5. Then we have the icon LAM-D2 ensemble with 2 kilometers. So all of this will remain. And in addition, we will have this SINFONY Rook ensemble with basically what I said already, improved data from Nowcasting, also satellite data, 3D radar data, and so on. And this run will then also be available about 45 minutes after the actual date and not 1 to 1.75 minutes after initialization. Concerning the SINFONY products, so we work on seamless probabilistic products that combine the nowcasting and NWP EPS information from 0 to 12 hours. And these products will then, for example, allow to determine the exceedance of a precipitation threshold, the probability of occurrence of a convective cell, or also the most likely amount of precipitation that can be expected from a precipitating convective cell. And here is a first example on a grid-based seamless product. So this is a combination followed by a method that has been developed by Daniele Nerini in 2019. He is working at Meteo Swiss. And for this combination, the model ensemble is used as an observation for an ENKF data assimilation on the nowcasting ensemble. So it means that the ensemble of nowcast is pulled toward the ensemble of NWP members with progress and time, and this results in an ensemble of combination members. On the left-hand side, you see the nowcasting ensemble member. On the right-hand side, you see an ensemble member from the Cosmo at that point still. And in the middle, you see kind of this transition between the nowcasting and Cosmo model. So this is just the first example. We are also working on other techniques here, and we also work on a seamless combination of the object ensemble, object-based ensemble, but that today due to time. And when you remember the first plot I showed with the skill or the score plot we used to explain SINFONY, so this is the first realization on how this could look like, or how this actually does look like at the moment. In black, we see the Cosmo EPS here. The blue is the radar extrapolation, so the nowcasting, and the red is this ensemble Kalman filter combination I just explained. And so it's a spread-based combination. It kind of puts together the best of both worlds, but the skill is not guaranteed. And it works better for periods of decaying convective activity and less good for growing convective activity, simply because the growing aspect is not really captured well yet. So that's part of the SINFONY model. And the second part of the presentation, which will be also shorter, I briefly want to present on our work to establish a vivid user exchange along the value chain. So one of our customers will be the flood forecasting centers in Germany, and the flood forecasting here is organized quite differently than in other countries. So it's organized on a state level, not federal. So basically we have 16 different departments working on flood forecasting. There are also other flood forecasting centers for specific rivers, I think for Rhine. And this also means that all of these flood forecasting centers have pretty heterogeneous capacities and use different forecast information already. So down below you see a kind of overview on which kind of deterministic on the top from DWD, other deterministic forecasts and ensemble forecasts are used by the different state flood forecasting centers. So you see some of them use ensemble forecasts, some don't. In some cases, there are only 2 people in these flood forecasting centers. Others are pretty well equipped with staff and also technical capabilities. Some do already provide forecast uncertainty information and others don't. So this means we are focusing on a group that is pretty diverse. And we are now working on establishing a user exchange with them. On the one hand, we are working on a systematic assessment of the user capabilities through a questionnaire that is currently developed also in collaboration with Vexicom from the Hans Ertl Center and Martin Göber in Berlin. We are developing a communication platform for user exchange. which can then also be used to provide examples of products and provide room for discussion. We are developing and establish a continuous dialogue between developers and users on the requirements, the possibilities and limitations of the new forecast products. We also aim on running user workshops at one point when it's possible again. And another important component is also the training on the use of probabilistic information and support the users during the implementation of the new SINFONY information into their decision chains. And due to the very diverse capacities of these flood forecasting centers, also turned out that not all centers will be able to deal with the full ensemble output. And they requested to get information that has been pre-sorted or grouped already. So this means that we develop so-called pseudo-deterministic products that condense the information provided by the full ensemble into a set of, for example, representative members, identifying the most probable development and so on. So the approach here is to explore different methods of clustering and then selection of representative members and so on. But this is work that has just kind of commenced and it's still in a pretty early stage. So I don't have anything concrete to show here at the moment. So let me come to the summary. With the SINFONY, we are developing a new coupled probabilistic system of radar-based precipitation advection, nowcasting, and very short-range NWP on the convective scale. This is conducted in a pilot project at DWT, which focuses on the one hand, basic development and improvement of NWP and nowcasting. So both of the methods, but also a combination of them. We focus for now on strong summertime convective events. Our customers are the internal DWD warning process and flood forecasting authorities in Germany. The first combined products of nowcasting and NWP ensembles for precipitation and radar reflectivity, and also for convective cell objects. For most of them, we have already developed some first promising prototypes, and we now enter the phase of consolidation and a step-by-step operational introduction until 2023. And there are also other research and development activities going on. If you're interested in further information, you can go to our website, dwd.de/symphony. And on top, there is a button where you can also switch to English language. And there you can find an overview also with some project descriptions for the individual activities that are part of the project. And with this, I'd like to thank you for your attention and also give you a brief glimpse on who is standing behind all the activities. So we have a pretty good and even growing team at DWD. And yeah, thank you for your attention.